So we have a slightly tricky situation. Our projector isn't talking to this computer. So we have a different computer that's running that. I'll be monitoring the Zoom and changing the slides, but we'll just have you.
Oh, I don't change my own slides.
You will change your own
Yes,
slides.
I like
Yes.
to. Okay,
So this will be the screen for a while and then we'll switch it over here to this PowerPoint.
let's take it to PowerPoint. I don't like it myself. Ugh. Okay, there we go.
Let's.
Oh, we can put a pretty picture on it to while people wait, like one of those beautiful.
We will as soon as the club meeting starts.
Oh, okay.
Yeah, we'll share your screen.
All
We'll
right.
make this all happen, but it's here. And when we go to slideshow, once we start it, all you have to do, you can just hit the enter button, like you said,
Okay,
forward, backward, up, down, whatever you want to do.
all right.
But if you would prefer it, I'm happy to take care of
No, I think that,
stepping in to get the screen sharing going.
oh, yeah, do it. I can't do anything but hit return.
Okay, I will take care of things from the Zoom end then.
Okay.
It's already recording now to the cloud. I took care of it.
Oh. All right,
So,
and, okay, so my.
yeah, get your stuff all set up.
Okay, good, I think,
And you're actually live on Zoom right now to several club
Oh.
members. And your talk will go on YouTube later. So,
oh, okay. Do I have a place to put this like a stool? I guess that's what it is. Okay.
sorry.
Oh, sure.
How will this work?
Oh, good.
Your favorite. This one. Yeah.
All right, well, that's good, that's fine. Oh, good. Great.
What do you think? Okay.
I get to introduce you.
All right. Go for it.
Run the meeting.
Okay.
Are you starting?
Yeah.
Okay.
It is fun.
Yes.
All right, turn me on here, dear.
You're already on. Oh, the microphone?
Microphone is on. Can you? All right, well, I'll just talk loud. Hello, everybody. My name is Ron Heron, Vice President. I'm here for the president to do my skating routine. And this very short Italian gentleman who's very knowledgeable behind me, who is our speaker. There we are. Let me just say that we've moved into the bigger room because in the last, give yourselves a hand, sure. Stargazers. People love astronomy. Back in 1963, when I graduated high school, that was the year, 60 years ago, that quasars were first, I guess, discovered and seen. And something else that was a mystery brought up by my science teacher, I recall that comets always going around the sun had a tail that faced away from the sun, and science didn't know why. And I, as a kid, I said, well, I know why. It's the solar wind. It just, oh, okay. And now that's pretty much well known. But quasars is still out there as far as being, galaxies that are whole stars or something. That's probably one of the different theories kicked around. I just wanted to say that we're going to have a great summer. And I thank you. We may or may not be down in Farrenhall next month, depending on what happens. But we're now here in our new digs, man, Flashman Auditorium. Next month, I have another one of those rising young super stargazers from UCLA, whose name is Hegby, Saheem Hegby, and he's very, very good. He's going to drive up here. He's going to show up and be either in here or in Farrenhall. On August the 4th, next month is July 7th on a Friday here at the museum. August 4th, our speaker is a former local professor who happens to be in attendance. Peter Love, are you here? Raise your hand. Why don't you stand and let's give this man a hand so he does a good show. Yell out what your topic's going to be in August. Oh, update on the James Webb. It's shaking things up. Our guest speaker may be talking about that because some of the pictures that's been taken is in his neighborhood. So without further ado, I do not have a lot on the background. I did try to look him up and all I could find was Dwight Hall and his phone number and the email address. And I'll let him tell you about his background. I will just say that Dr. Robert Antonucci, who is known as Ski among his beloved students and personnel out at the university, is an expert on quasars. He's been checking them out for a long time. He had a article back in 2013, March of that year, which is 10 years ago, on active galactic nuclei, AGN. Remember that, AGN. He'll use that term a lot. The name of his article was, I think, what was it? Supermassive? No, Quasars still defy explanation was what it said in Nature magazine.
The title is at the discretion of the editor, but that was okay.
And don't go to the article afterward. He posted it on most. Hopefully you all got it, but there's one right past it called "Scientists Are Snobs."
Yeah.
I didn't read that one. Nevertheless, quasars defying explanation. What the heck are they? Were they? Supermassive black holes are common in most galaxies. This is a quote. These are some of the things in the articles in case you missed it. He ended the article by saying, I urge my junior colleagues to spend 15 minutes a day, please, thinking palms down and eyes on the ceiling. That's just about 3% of their time. As I saw recently on a California bumper sticker, don't just do something, sit there. I'll let him explain that to you, ladies and gentlemen, to talk about quasars. Ski. He's a skier and he's beloved and he's been here for a long time from the University of California, Santa Barbara, Robert Antonucci.
So I'm sort of a
I'm just gonna slide on in here really fast. So sorry, everyone. We're just gonna share the screen for our Zoom people at home. Let's see. And there's no sound, right?
well, right, there's no sound in the presentation.
Okay. There we go. And I'm gonna make this small so you can see your screen. Everything look good to you?
Yep.
Okay, great.
We're
Sorry.
ready. Yeah, I'm a known, well, I don't know. I could say I'm a known crank, but I don't know if that quite does me justice, but I think that that's probably somewhat of a widespread opinion. In this, I tried to get you guys to do a lot of work before I came because I want you to understand what I'm saying. It's complicated. But there are two real themes in that article. If you read, it's only 2 or 3 pages, 50th anniversary of Quasars, you know, and Nature magazine. And I think they were very surprised at what I gave them, but they said they'd publish whatever it was, you know, and especially because I only gave it to them at the very last minute so that they couldn't change anything. And part of it is a straight, you know, with the numbers review of high points in the history of the field. But then there is a sort of ever increasing tone in that article of like anger and criticism and like when I saw, when there's an article like that, then secondary sources like Scientific American or whatever pick this stuff up and they, digest it and they ask some other people about it. And my favorite reaction was, I think it was New Scientist. They talked about this, very unusual. I'm the only one that really criticizes people. I mean, I just can't tolerate, sloppy thinking or not knowing everything that's out there and so on. Anyway, it was perceived as, super critical. And but my favorite thing was in New Scientist, they talked about this Nature article, and then they asked, as they always do and should do, several other random astronomers about what they thought of it. And I was thrilled. I couldn't believe it that of the 3 astronomers that they asked about it, 2 said they wish to remain anonymous. Now, I've never seen that before in this field. I must be perceived as like the danger. And I mean, I was thrilled. There are 2 people in this world that are afraid of me at least, which is, gee, I thought that was great. Yeah, so I'm going to tell you a complicated story, which is why I wanted you to get a little heads up. Now, if you don't remember all the details, you'll get the flavor of it, because each little argument is not difficult, but a lot of them. Oh, you're talking to the mic. Could you hear me? Oh, thank you. Thank you, ma'am, Miss from the anyway. Ma'am, she's all right. So I'm going to tell you that it has something that fit together wonderfully. It's incredibly robust, has amazing predictive power, universally accepted as setting the scene for supermassive black hole accretion in the centers of galaxies. But at the same time, in a sense, it's sort of trivial because it doesn't speak to what happens at ground zero. And depending on how far I get, I may tell you about that. And I think that there were 3 breakthroughs in this field since the discovery in 1963 by Martin Schmidt, and 2 of them are imaginary, sadly. The one that is not imaginary is a fundamental prediction of the supermassive black hole accretion hypothesis for quasars, is that you will see concentrated, super concentrated masses. Now we have pictures of a couple of these supermassive black holes that show that dark center, which is absolutely definitive. For black holes, we also have gravitational waveforms of merging black holes. So they're absolutely out there, and accretion power is everywhere in astronomy. So that is all that is true, and most of the quasars that we see are very distant, which means they're in the early universe, right? Of course, the distance equals time in astronomy, as you all know. And when you look at something really far away, you're looking back in time, and back in time, there were lots of powerful quasars. And then, so another fundamental prediction was, as far as we know, the only difference between the distant universe and the nearby universe is time. Probably the regions we see in distant parts of the universe, if we were there today, they look like us. as far as we could tell, and they would look at our galaxy and it would be a quasar and so on. So, so where are the quasars today? In other words, all the galaxies that are in our region of space were quasars in the early universe, but we're seeing them as they are today. Well, they've already eaten almost everything they could get their hands on, and now they're quiet and they're just sitting there. So great prediction was ordinary galaxies today, like the Milky Way or Andromeda, they should have leftover supermassive black holes that may be asleep, and but they got to be there, and you can with good equipment, the space telescope and so on, you can identify those huge masses in the centers of every galaxy, and that totally came true. So the notion of supermassive black hole accretion is certainly right as far as that goes. Now, let's see. I was going to, now if I have time, I will tell you about, magical thinking in science. And I hate to do that because this is my tribe, and I'm not proud of some of the thinking, that goes on. I mean, basically, in my opinion, the problem in science is the bad ideas hang around too long. Does anyone follow Alzheimer's research? Now, that's a serious problem. And they have been stuck on this protein plaque thing as a causative agent for the last 40 years, and they get zero therapeutics, and hello, and at least in astronomy, it doesn't matter. That's the beauty of it. That's the beauty of it. All right, so slow down. Well, all right, slow down. All right. Did you ever try this stuff? Amitrol. The instructions are take one capful every 15 minutes to forestall vomiting. Wow. And it's hard to believe, an hour ago, I was worshiping porcelain god. Excuse me. All right, but the show must go on. All right, now, boy, there's so many things to say. Basically, if I don't talk fast, how can I say all these things? Well, quasars, when I was thinking about what to go into for my research, they have a lot of super attractive aspects, but one thing you may know that a quasar can be 1,000 or 10,000 times the luminosity of a whole galaxy of hundreds of billions of stars. It's completely ridiculous. And not only that, but do you know that if an object's luminosity varies quickly, it must be small? You don't know that? Okay, let me explain that, because this is a very, very powerful argument in astronomy. Consider the Andromeda galaxy, a companion. It's 100,000 light years across. Okay. Suppose all the stars in that galaxy doubled in brightness instantly. Now, for a while, we wouldn't notice anything because the light in the brighter state has to reach us, be another, million years or almost 2 million years. Then what happens is we get to a point where we're seeing the nearest stars in Andromeda in the bright state, but most of the stars in the galaxy still in the dim state. Let me see if I can say that a little more carefully. Suppose the center of Andromeda is 1 million light years away. The near side is 950,000 light years away. The far side is 1,050,000 light years away, right? You with me? So if all the stars double in brightness for 950,000 years, we don't notice anything. And then the next year, we're still seeing most of the galaxy as it was in the dim state, but the very closest stars, well, the delay is 950,000 years. So we start to see a few of the stars in the galaxy in their brighter state. And we don't see them all in their brighter state until another 100,000 years go by. Because the far side of the galaxy is 100,000 light years farther than the near side. I don't know if I said that very, very well. Think about that. I can talk about it afterward. I don't think I explained that too well. The point is, though, that even if an object 100,000 light years across suddenly doubles in its luminosity, for us, when we see the luminosity rise only gradually, and it takes 100,000 years before we see all the stars in that galaxy in their bright state. Does that make any sense? It's very important because, you know, when pulsars were discovered and we saw that their radio waves, they were flickering in a tiny fraction of a second. And that instantly proved that they were less than, you know, a millilight second across. It proves that they're extremely compact. Well, we couldn't see them change their brightness so rapidly. Well, so not only were the quasars as bright as 1,000 or 10,000 galaxies, but they flickered over timescales of weeks. So their size was infinitesimal compared to a galaxy, much less than, basically solar system sized. So you're getting that much luminosity out of something solar system size, a tiny fraction of the distance between us and the Andromeda galaxy. So that made them exciting. And also we could see them. They were so powerful that the reason it was so hard to discover them and took Martin Schmidt to discover them is people looked at their emission lines. They have emission lines and they didn't recognize them. And then Martin Schwarzschild finally realized the reason why we don't recognize this pattern of emission lines is because they're really ultraviolet lines and we've never seen them in the optical before, which means since they didn't have orbiting observatories, it means that they'd never been seen by astronomers before. And that is what I call, you know, childhood's end, in the sense that the redshifts of all known objects before quasars were tiny compared to one, which meant in the expanding universe, we couldn't probe significantly back in time. But all of a sudden the quasars, you know, boom, there, now we got the whole universe to explore. Well, let me, oh boy, this, all right, I better get on with my story here. Let's see. Okay, so when I'll show you another amazing thing, the apparent faster than light motions in quasars. But okay, let me, how do I go to the next slide? Let's see, oh, return. Space bar, see, that's all I know how to do. Okay, let's learn some spectroscopy. You know, I'm gonna have to watch the clock because this is kind of crazy. Is there a clock I can see? Because I'm afraid to see. You know, I could, it's complicated. All right, let's learn some spectroscopy. I won't get through much of this, but you'll get the flavor. Let's learn some spectroscopy. And here's the spectrum of a quasar and the spectrum of something called a radio galaxy. And this spectrum shows emission lines, which means that there are either ions combining with electrons and having a recombination cascade of emission lines. That's what some of these are. And can I point to this? Do I have a pointer or anything? Oh, I can do it by hand. I could just walk over there. I know, but then I'm not. Okay, good. Oh, okay, good. Yep. Okay. All right. So, yeah, I do, because this I'm obviously already completely well.
What's your timer?
Oh, anything. I mean, I'm really I shouldn't have gone on these descriptive digressions, but okay. So here is the spectrum of, well, a radio galaxy. See, basically after the Second World War, there was all this leftover radar equipment, and it fell into the hands of astronomers, and they started mapping the sky. And in radio waves, instead of the sky looking like, you know, the stripe of Milky Way and stars and so on, the stars don't emit radio waves. Instead, what you saw was the sky was filled with circles and dumbbells. And the dumbbells, which I'll show you, are clouds of synchrotron emitting plasma, meaning relativistic particles and magnetic fields, hundreds of thousands of light years across. I'll show them to you. You look at it, and what you see is nothing in the optical at the positions of those clouds, but in between, there's an ordinary looking galaxy. But if you look at the spectrum in the very center of the galaxy, you see things that are not ordinary. You see signs of hot ionized gas, and it produces emission lines. And what I want to try to get across, although this is sort of an advanced physics concept. Okay, this is this little line. It's called H beta, and it's from hydrogen atoms decaying from second orbital to the fourth orbital to the second orbital. These two are, you know, when they were first observed, people didn't, they had never seen these emission lines in the laboratory before. And you saw them in nebulae. So this was called nebulium for a while. But they're really from doubly ionized oxygen. And for the physicists, it's because these are forbidden lines, and meaning that in elementary quantum mechanics calculation, you find that the rate at which these transitions should occur is 0. And then you look at it more, and it's never been seen in the lab. But if the density is very low and the mass is very large, like sometimes in a nebula in space, then these so-called forbidden lines show up. Now, if you see these emission lines, a spectroscopist would say, well, there's an ionized gas recombining hydrogen, and these transitions are excited by collisions with other particles. The fact that you see strong forbidden lines means that this is a very low density gas, not like a laboratory gas. Now, you know that an emission line of a given transition should always would always have the same energy according to quantum mechanics, almost exactly. But these lines have some width to them. Some of these photons are a little bit redshifted and some are a little bit blue shifted. And that's okay. That just means that there's a collection of ionized gas clouds, and some are moving towards us and some are moving away relative to the mean speed for that galaxy. So the width of this tells you about the motions of the ionized gas. So here's a little signal that in a radio galaxy, there's something going on. And now let's look at a quasar. A quasar has the exact same thing. Here are these narrow lines, forbidden, and see this little spike? But here's the difference. This line, this is a permitted line, which means that it's very strong in a high density gas. And it appears at the base of the hydrogen line, but not the base of these forbidden oxygen lines. Just to get the flavor of, don't worry about it, but this says that there's another family of ionized gas clouds that is not present here, and it has different properties. One, high density, because it's strong in permitted lines, but not forbidden. But two, this line is very fat. This photon here is red shifted, this is blue shifted. These clouds are moving at many thousands of kilometers a second. So the difference in the quasar and radio galaxy spectrum, there are two differences. One is the high density, it has this extra family of ionized clouds, but also, even more important, this continuum in the radio galaxy is nothing but the combined spectrum of the stars in the galaxy. But, oops. Okay, so I don't know how that happened, but the quasar also has a more important difference. It has this very powerful continuum source, as I said, equivalent to thousands of whole galaxies and highly variable. So, forbidden, well, all because if you calculate there, you know what, who knows what quantum mechanical selection rule is? Does that sound familiar? Okay, if you do a certain calculation in quantum mechanics to determine the rate at which that transition occurs, you find that the rate is zero. And they were never seen in the laboratory. They violate these so-called electric dipole selection rules. And to a good approximation, their rate is zero, and they were never seen. But because conditions are so different in astronomy, and extremely rarefied gases with high masses, they can show up. But they were, as I said, they were called nebulium because people didn't know what the hell they were. That was some new element. All right, let me, okay, so now we look at these double radio sources, like here. Oh, I really wanted the previous one, but that's all right. Oh, hit the back button. Okay, there. Okay, I'm hitting a left-hand arrow. Oh, there we go, good. Okay, yeah, oh, but now it's correct here, but not there. Oh, okay, okay. So people started looking at radio waves from the sky and saw these dumbbells everywhere. And sometimes between the two bells, there was a galaxy, and so we call it a radio galaxy. Now, the energy content of these clouds is incredibly high. And where did it come from? Well, it can't be a coincidence that that galaxy is right between the two, especially because it's repeated over the sky. So there must be something in that galaxy, in the center of that galaxy, that is sending energy out into those clouds. And let's see, I got this correct here. Oh, there it is. These are beautiful. This is a modern picture, you know, that shows very, very clearly that these clouds are connected by tubes into the very center of the galaxy. We call them jets. So certainly the visual impression is there's some energy source in the very center of the galaxy that's shooting out energy into those beautiful clouds. And all those other images there are distant galaxies. So let's see. Well, these are all, I could look at these all day. I was so intrigued. You know, some of them look like this, you know, but most are pretty. Okay, here's the first such picture. 1953, the most primitive. This is one of those beautiful radio galaxies, what it looked like in 1953. They just figured it out how to do this. But now, okay, now I'm not going to be able to go into the details. That has a subtle difference because it's quasar instead, but I gotta. Now look at this here. It looks like one cloud is being fed by the center, but not the other one. So what's that all about? A lot of mysteries. Now look at this. This was Billy. An amazing discovery. There's a kind of a quasar called the Quasar. And when people first looked at these, you know, if you just saw one little dot, not two big clouds, but just one point where radio waves were coming from. One super bright point. And that was using radio arrays that were tens of kilometers across. If you combine radio telescopes at great distances, you get very high resolution, like in the supermassive black hole picture. Well, these were some of these bright sources called blazars, and using, quote, very long baseline interferometry, telescopes all around the world, it was possible to zoom into the center, and on a scale of a few light years instead of a few 100,000 light years. And what they saw was a stationary spot emitting radio waves and a little chain of dots. And you go back next year, and these dots have moved. And in 6 years, this dot has moved from here to here, which is 30 light years. So in 6 years, it looks like it's moved 30 light years. Now, that's what we don't expect to see, right? And so that intrigued me too. And there was a possible explanation for this. And I wanted to check that explanation out. And so these are things that got me into this field. And okay, now this is gonna be pretty hard. Let's see. Okay, yeah, this is too complicated, of course. But let me okay. Here's no. Here we go. I'm gonna get this point across. Okay, when I was in what's that? I got to go back one. This, yeah, well, I thought maybe, okay, here, this is what I imagined. Yeah, certainly. Spectroscopic unification with polarimetry. Now let's, I'm just going to give you the flavor of that, I guess. We're not going to go into great detail, but let me tell you what I found. A quasar looks like an extremely energetic object, whatever it is. It seems like it's probably macho enough to power 2 giant radio lobes. But in a radio galaxy, you looked in the center and saw nothing, except for some emission lines. But emission lines that's clouds that are reacting to an energy source. That's not an energy source itself. When I was in grad school in Santa Cruz, there was a fellow named Joe Miller there, a professor, and he had an idea. He had a postdoc. He was working on a type of instrument that was completely novel. You know, a spectrum tells you the intensity of light at each wavelength, but light has other properties besides intensity. Polarization, linear polarization, and circular polarization. Here's what that means. Most light sources are unpolarized, meaning photons come towards you. They have a transverse electric field, but some of them will be going, if they're coming towards you, some will be oscillating like this and some like this. An even mixture of all angles. That's unpolarized light. But when light reflects off a surface or off a particle, it becomes polarized. And that's why you have Polaroid sunglasses, because sun that reflects off your windshield comes towards your eye, and all those photons are oscillating horizontally. Ones that were reflected off the windshield. So if you cleverly wear Polaroid sunglasses that block horizontal light, boom, the glare is gone. So a reflection polarizes light. And the way it works is here, suppose a photon is coming up vertically, and here is an electron. And if the photon's electric field causes the electron to oscillate transversely, it may scatter that photon towards you, and it will arrive oscillating horizontally. So here's the photon coming vertically, but it's a transverse wave. So the electric field is going like this. Shakes an electron like this, and the photon comes to you. That photon is oscillating horizontally. And I won't, I guess I won't take the time to go more because I'm going to get somewhere, but you're not going to get every bit of this because I was, it's just too much. Let's okay, so here is let's see. Yeah, see, this is not helping me maybe because that is really overkill. So let me just tell you this. Joe Miller and this postdoc, Gary Schmidt, who I hated, and who hated me, we're building an instrument that sorted the photons by not just wavelengths, but by polarization state as well, simultaneously. And why were they doing this? I think it was a hunch, they were thinking, well, everyone's been studying the intensity of objects, and who knows what is encoded in this polarization signature. And I think it was, they were going fishing. I think they wanted a free lunch, and they wanted to take a, see what was out there, because that was really an unexplored aspect of light, almost entirely in astronomy. And I remember, Joe Miller would show me this instrument. He was so proud of it. And I looked at it, and to me, it just looked like every other gray metal box of parts I've ever seen. And I just nodded, okay, Joe, and, he realized I was hopeless and I was going to understand that. And I wasn't a great observer either. When I went to the telescope for the first time with the two of them, the Lick Observatory, I just prepared like crazy and had these incredible checklists. And I'm starting off the telescope and I read open dark slide. Right? If you've ever done astrophotography or anything, you know, you have to open, there's a dark slide to protect the detector. And you got to open it up to get the light through so you can analyze it. And I said, open dark slide, and opened the dark slide. And, you know, the other two people at the telescope were super intuitive about it. They wouldn't have. I learned later that after that first night, the postdoc, Gary, said to my advisor, Joe, you got to get rid of that guy. Did you see? He had to read his checklist to find out if open the dark slide. Yeah, so all right, so radio galaxies, what's going on? Why are radio galaxies different than quasars? How come there's nothing in the center? Well, I discovered that almost all the continuum in the radio galaxies is starlight. Let me go back. Whoops, I think I'm, let's see, takes a little time. When I know, but I have to keep going. I want to get back to the spectra. And well, I wanted to show these one more time, because then there's like literally the surprise of my life, which I will tell you about. I can't go back. I can go back up here, but oh, there we go. Okay. Okay, here. All right. Now, okay, so there, without caring about the physics, the top one is a quasar. And the bottom one is a radio galaxy, and all that continuum is just starlight. But I noticed that gradually that in the radio galaxy cores, there was just a little trace of light that was not starlight. And I realized gradually that it was polarized, and that meant that it was reflecting off a natural periscopic mirror. And it was going to let me see that radio galaxy from a different direction in space. It was going to let me see that galaxy from the side. Now, astronomy is very strange because you can't do experiments and you can't even walk around to the side of something. You know, a car doesn't look the same from the side as from the front. If you had those cars in the sky and you study them, would you ever figure out that's the same thing? Well, eventually, but it's not that easy. So this is the radio galaxy, shows these very strong emission lines. Yeah, I'm going to skip this slide. I go to a more friendly one. There, okay, wow. See, this is a radio galaxy, narrow lines, forbidden lines, narrow, permitted lines. But I noticed that there was a trace of light that was polarized and perpendicular to that radio axis. And I realized that I was going to be able to look down from the radio axis and see what the radio galaxy would look like if I were in a different direction in space along the radio axis. And I separated out those polarized photons, and the result was, surprise of my life, basically, that now these permitted lines are strong and broad. It's a quasar. So it must be that the photons can come out from a quasar along the axis of the radial lobes. And if someone had looked from that direction in space, they would have seen the quasar. But from our direction, the only way we could see it is to pick up a little scattered light off a little natural periscopic mirror. And now we could see things from other directions. And, you know, that was epic. No, I mean, we were dumb. I mean, but it was a while to figure this out. Well, you know, that's how you know you've made a really good discovery, is if afterwards you feel really dumb. You know, because it meant it was basically important. And all right, now I'm going to tell you how we explain superluminal motion, and that's as far as I'll get. And I won't have to tell you about magical thinking and embarrass myself or my tribe here. Okay, here's the explanation that, you know, I wanted to work on. Totally, it's settled now. Here's the explanation for superluminal motion. Nothing's really going much faster than light. Here's what's happening. Suppose I'm 10 billion light years away from you, and I hold up a clock, strikes 12. 10 billion years later, you see it strike 12. Okay, I wait an hour. After a 10 billion year delay, you see it strike 1, right? Everything looks normal. Now, what if I took that clock when it struck 12 and threw it at you at almost the speed of light? Then, when the clock struck 1, it would be closer to you and have less of a light travel time delay. And the result is the image of the clock striking 1 would arrive at your telescope right after the image of the clock striking 12. See what I mean? Less light travel time. It's sort of like a Doppler blue shift, but where each wave has less travel time, and so they look like they're bunched up. The clock striking 12 has a 10 billion year delay, and then you see it. But by the time it strikes 1, it's almost 1 light hour closer to you. So it strikes 12, then strikes 1, like right away. Now, if considering these apparent faster than light sources, so far we haven't explained anything, because if I throw a clock right at you, well, there's a time-lapse photography effect, but that superluminal motion is a sideways motion, right? It's not a motion towards you. But you got the idea that there's a time-lapse photography effect. And you can show, which I give this as a problem, you know, you can show that, suppose I have a jet, something moving at 0.99 C. If it's going sideways and you measure the speed, you get 0.99 C. The light travel time is not changing because the distance isn't changing because it's moving transversely. If I throw it right at you, you don't see any speed on the sky, but if it's a little bit off, a few degrees off from exactly towards you, then if you do the geometry, you'll see it'll go 10 C. So it was proposed, and let's see. This is my clock here. Oh, okay. So it was proposed that by Martin Rees and Roger Blanford, that superluminal motion was an illusion. And they went farther than that. They said, not only is it because a cannon is being shot right towards you, but off by a few degrees. They said, what are those cannons? They said, well, those are the giant double radio galaxies and quasars, because a few of them, you simply must by chance be looking right down the barrel. See, in other words, they said, okay, we can explain superluminal motion if there are cannons sending cannonballs almost towards you, but not quite. And then you would say, well, okay, fine, that seems a little funny, but what are those cannons? And what about the ones pointing in the other directions? Well, they said, look at those jets connecting the centers of galaxies, supermassive black holes, to those lobes. There's plasma zooming out those jets. It might well be going 0.99C. Some of them, you're going to be oriented just right to get the superluminal effect. And Roger Blanford presented that at a meeting. So there on the left is the normal giant double quasar or radio galaxy. And Jim Condon is a radio astronomer, and he's trying to make sure he got this right. Now, the jargon's a little different here, but here's what he's asking. He drew this on the board, and it was all dutifully copied. He said, if these superluminals, which they call BLAC here, if they're normal doubles, where you're just looking down the jet, he's saying, you wouldn't see two clouds, but you'd see one cloud projected on the other cloud. See what I mean? A dumbbell like this. And so he draws this. He says, I know if you looked at it from the side, you'd see just maybe one blob, but you'd see something. And Roger says, yes, that's right. But what Condon knew was that this diffuse radio emission that must be present around this bright core was not seen. It simply wasn't seen. But this was a case where the theorist understood the observations better than the observer. And what Roger Blanford said was this: you have this really bright source. Special relativity says if something's coming towards you at almost the speed of light, the light is focused forward like a beam, a flashlight. And so that central spot and those moving spots are extremely bright. And Roger said, the problem with you radio astronomers is your images have poor dynamic range, meaning if there's something very bright in the picture, you can't see the fainter things. And, you know, well, that was an excuse, you know, I don't know how, if it sounded lame or whatever, but soon after that, radio astronomers discovered or developed a mathematical algorithm which would solve the dynamic range problem called self-calibration. The dynamic range problem is ultimately due to air blowing over the antennas. And at that point, you know, I was reading this and I was just at the edge of my seat and I thought, I have got to look for those big clouds, you know, the one globe in front of the other. I got to look for that. Now we can look for that. And they were all there. And we made some very strong arguments that really nailed this and said, yeah, that's definitely what's going on. So I think I'm about out of time, but that's some, you know, some very nice, lovely, successful things that worked out and had great predictive power. And the trouble is, everything I told you is, a little away from the black hole. So can't we, what we really like to do is see the black hole. Now, the black holes that you've seen imaged in the radio are fabulous, but it's just a little faint glowing ring because they have very little matter around them. So they're not like a quasar. They sure as hell prove, in my opinion, that they're black holes, but they don't tell you how a quasar works, which must be eating copiously, from its surroundings. Well, if I had an infinite amount of time, I would tell you the going theory for how a copiously accreting supermassive black hole produces its light, and I don't believe it, but we don't have an infinite amount of time. So let me stop there and ask for questions.
Really enjoyed your articles.
Okay.
10 years ago.
Yeah.
Gotten any better?
Have things gotten any better in 10 years? Well, now that's a good question.
You were saying that the people were just publishing things where they knew that they were wrong.
Well, have things gotten any better? Yeah. I'm just close to finishing a very long article on all this stuff. And I think I'm making a dent, actually. I'm almost the only, dissident there, but I think I'm making a dent, but it's puzzling that, people have said to me, astronomers have said to me, okay, so this model isn't correct, but, we'll use it till something better comes along. And it pisses me off. And I say, nothing better is going to come along unless you can put that out of your mind, put your hands down for 15 minutes, 3% of your time, and look at the scene. That's what some of you knew Stan Peele have predicted the volcanism on Io, and among a million other incredible accomplishments. And I miss him so much. And I'd asked him about that. And he said, I was doing my job, I was in my chair with my feet up on my desk, looking out the window at the moon. That's a job. And I was wondering, if the Earth's tidal forces heated enough inside that vessel would center. So this is our job. So that's just wonderful. And it's an incredibly hard problem. We spent months on it, and the answer he came up with was no. And but you never let a good idea go to waste, because then he started thinking, well, maybe there's some other context in which the tidal heating is much greater. And he started thinking about the satellites of the outer planets and how they would really get like. And he realized that there's such an amazing dissipation of energy in the center of Io that it would just be covered with volcanoes and geysers all the time and so on. Okay, but getting back to your question though, and also of course, the Io is super hot, but you go out to the next one, Europa, and it's just hot enough to have a very deep liquid saltwater ocean. So, and that's by far the most hospitable place for life. There are plenty of Earth extremophiles that would be very content there. So it's so profound. But yeah, I mean, see, here's something I can prove in this paper that I'm writing now is that you can't observe most of the light from the quasar because it's in the far ultraviolet, which is not only hard to get at, but our Milky Way galaxy is opaque in the far ultraviolet. So you can't possibly see it. But I figured out how to show and I can prove that all of these optical UV sources and the different objects have a very, very, very generic character. And that suggests to me that atomic physics is at work rather than some self-similarity. Well, they're very generic. They and I can, if I had a little time, I could tell you it's not that complicated, but it's very, in fact, I was so obnoxious in this paper that I gave this argument, and if you know this field well, you know that it's bulletproof. And I didn't carry it out. And I just, partly because I've already disproven, well, and I just arrogantly said, we're going to leave the actual demonstration as an exercise, because I've become such an asshole. But it is, it's a bulletproof thing. So, I don't know why it takes so long to get, there was this, the idea of a paradigm shift in astronomy, or in science, Thomas Kuhn, and I was thought, he said, he argued that the way science works is everyone's working under one sort of paradigm, and they're all like, gerbils or something. And then when there's a paradigm shift, there's some sort of consensus or something flips, and they say we're going to something in a different paradigm. And I always resented that. And I thought, gee, come on, we're not gerbils, but I think we are gerbils, just to a significant degree, unfortunately. It's very frustrating. So anyway, let me go to my very fast last conclusions. Sorry, let's see. I have, I could have a lot of cool things here, but what can you do? Here's my conclusion. Yeah, as I said in that article, what's the problem? Why is it 50 years? We don't understand this thing. And is it because we're too dumb? Or, that's totally plausible. Maybe we don't work hard, maybe we're just like drinking beer all the time, or maybe we don't have a good telescope, or whatever, or maybe we're not. I don't even think creativity is as rare as critical thinking. Yes.
What's the difference between a regular galaxy and an active galactic nucleus?
Well, if a
Star mass.
Yeah, okay, that's a good question. What's the difference between a regular galaxy and an active galactic nucleus? And if you look at the Milky Way, we have a 4 million solar mass black hole. And so instead of answering your question, by phenomenology, I'll just say that all the galaxies have supermassive black holes. And we could talk about how they evolved or whatever. And basically, they're just sitting there starved most of the time in the present day. But especially when we look far back in time, when everything was super close together before the expansion of the universe, and everything was chaotic and hadn't smoothed out, into orderly motions, they were stuffing their faces, and that, of course, no energy comes out from within the black hole, but on the way in, with the material whipping around and the magnetic fields, and they can make the jets and all kinds of phenomenology. So basically, the difference is the black hole is being fed. That makes what makes an active galaxy. And there's a really amazing, great thing that Martin Rees, this genius, astronomer royal at Cambridge University, predicted, and then, now it totally came true, and it's super great, is he said this, that in the modern era, the supermassive black holes are basically totally starved, except he said once in a while, a star far from the black hole will pass close to another star just by coincidence, and they'll be like two billiard balls, and they'll be reoriented. And he was trying to figure out, would the black hole ever get a launch at this point? And he concluded that with all the stars and their peculiar motions, he said every 10,000 years, one star will accelerate and, redirect another star so perfectly that it gets eaten by the black hole every 10,000 years, basically. And, in astronomy, if something happens every 10,000 years, we're not discouraged. We said, fine, we'll look at 10,000 galaxies for 1 year. Or 1 million galaxies for 1 year. We don't mind if it takes that. And they've been found, and they're just wonderful. And that's what's really going to help us understand quasars. I said astronomy, we don't do experiments, but sometimes nature does an experiment for us. And if I wanted to do an experiment to understand a quasar, I would say, let's start with a starved black hole and throw in one star. And that's exactly what these are. So they're really going to help us out. Yes. Oh, well, it's somewhat of a definition because historically a quasar, there are galaxies nearby that have like weak quasars. And so if we stuck with the historical definition, we would say in order to call it a quasar, it would have to be above a certain luminosity. See, quasar means a quasi-stellar radio source. So you just see one brilliant spot. Now it's in a galaxy, but no one could tell, historically, because it just had one super bright spot. And so then, but that definition of not seeing anything around the quasar became untenable as things got better. So in other words, it's sort of it's just that's got, if you're willing to accept a low luminosity version, the nearest radio galaxy, Centaurus A, is a mere 4 megaparsecs away, which is super close. It's only like a few times as far as Andromeda, our closest big galaxy. And it covers many degrees on the sky. It's huge. Anything else? Okay, well,
Dr. Robert Antonucci.
all right.
Thank you, sir.
Right.
Why do they call you Ski?
Well,
You're a skier.
I used to say only my mom knows, but
Oh, you're-
he doesn't even know anymore.
Well, are you from Italia? So
Yes,
it would be the
I am.
north, it would
Yeah,
be the
yeah,
Italian
yeah.
Alps, right?
Well, one side is from like Napoli and the other, I would say is.
Well, we know all about quasars now. I
Yeah.
felt like I sat through a big class out at University, Broida Hall there with Dr.
Yeah.
Antonucci. Listen, come back here. I got something for you.
Okay.
On behalf, before I give this,
Honorarium?
an honorarium, plus our priceless ceramic
Oh, boy.
cup that was
Wow.
minted by Chumash Warriors. Give him a hand.
Thank you.
Can you accept a little honorarium? Seth? There you
I
go.
was kidding. I didn't think there was an honorarium.
No.
Thank you.
I appreciate it. Well, you did good, and we gotta just say that you
This is
can
just
and
isn't this just the,
just print it out.
the thing that, the copy underneath where you trace? I don't think that's a real term.
I don't know. But cash it quickly. Our outrageously incredible outreach coordinator is over in the corner. Chuck, wave at everybody. He wants you to know next Saturday night, we're going to be gathering out here next to Palmer Observatory for our big Saturday night party. Ski is invited. All of you are invited. Thank you for coming tonight. Next month, we have a young UCLA student coming up here to talk to us. He's probably watching us right now on YouTube, on Zoom. We also have a Monday morning podcast. August 7th, no, August 4th is our friend Peter Love over here taking us out to the web. He's been following that. So don't forget, club, a lot of outreach. You can get incredible stuff like this incredible warm jersey jacket that keeps me through the winter. And of course, if you didn't know and you came late, members, actually everybody that wants to come early at 7 before this program starts, we go down and get comfortable in one of the warm fuzzy chairs at the planetarium named after Gladwin. This young lady here named Chrissy Cook runs the show, and we just have fun looking at the night sky inside. You're all invited. So on the 7th of July, you're invited back. Maybe we'll be back in here. Otherwise, thank you. Go on SBAU.org, grab some paperwork, and thank you for coming tonight on behalf of Jerry Wilson, our president. He couldn't make it. Thank you. I enjoyed it.